So on the agenda, I'm pretty sure Professor Ting was on the agenda to show up today. I did not win a Nobel Prize like Professor Ting did. And following Clay, I don't know if that's possible. So I apologize. I'll be much more boring than he is. AMS is a large hydrogen physics experiment that is sitting in the payload bay right now. This is a 1/25th scale of it. Because AMS weighs 15,251 pounds, I didn't carry it out there. I'll pass it around. Try not to break off a little pieces. We need it later. So AMS is looking for antimatter. Terry talked about this a little bit earlier. Antimatter, dark matter, and dark energy. But more importantly, what we're doing is put together an experiment that can search for the origins of the universe. We are actively looking at the physics of today and trying to decide, is it right? Is it wrong? Do we know it? What is dark matter? Why is the universe expanding faster than we thought it was? Why is half the universe not made of antimatter? Or is it made of antimatter? And maybe we'll answer those questions. Professor Ting likes to point out that over the last 50 years, major physics experiments have gone to funding agencies and they said, we're going to go find this. And they get lots of money and they go spend all that money, they build something big and new, and they don't find what they said they were going to look for. Instead, they find something completely different, something that they didn't expect, and they change the face of physics and they change the face of science as we know it. Maybe AMS will be able to do that for us. So I'm going to give you a couple of, we actually do have some electronic resources that you can go find us at. You can find us at ams.nasa.gov. You can find us at www.ams02.org. And I actually do tweet on AMS ISS. So I will open it up for questions. I don't know how much you guys wanted me to talk, but I think I'll just open it up for questions.
Questions, if you have a question, please keep your hand raised. I'm just wondering how long you spent planning and designing the AMS unit so that you don't hubble it, and have to do repairs. I'm sorry, there was an entire mission to repair it. I'm just saying, how do you try to prevent that? That's all.
Okay, that's a good question. And we learned a lot of lessons from Hubble. So AMS has been in existence since 1994. We flew a preliminary version of it on STS-91 in 1998. And we were originally going to fly to space station in 2001. However, the resting place for it on the space station wasn't even put up until 2007. So in the meantime, to give some physicists some time, they upgrade. The original experiment weighed 9,197 pounds. This one weighs 15,251 pounds. The upgrades have been extensive. What we do, though, because AMS is so sophisticated, AMS has 6 major detectors, a couple of minor detectors. We have 300,000 data channels, which means 300,000 wires going somewhere. It's not simple to make it plug and play. It's not simple to make it modular. So what we do is we make it fully redundant. In fact, multiple redundancy. So in our electronics, we have 4-fold redundancy. And put them in different places on the experiment in case something gets taken out by a micrometeoroid or some kind of orbital debris. Where we can, we make it accessible for EVA astronauts. When AMS is installed on space stations, it's installed using the robot arms, the shuttle arm, and then the station arm. However, we are set up to be able to go out and do EVAs, and we can go change out power lines and data lines in the event that we lose one of those. However, because there's no modularity, there's no changing out, the tracker of AMS. It weighs way too much. It's buried too deep. There's no way we can make it easy enough for an EVA astronaut to go out and change out.
Hi, my name is John. I actually work at NASA Goddard. So I have a deep question for you. Well, how could this potentially change science? I'm asking you to put your prophetic hat on and say, how could this change science based on what it discovers or finds?
Okay, so never before have we put a charged particle detector into space that has the sophistication that AMS has. We have launched some charged particle detectors, ESA's launched some charged particle detectors, but nothing to the level that AMS can get. And essentially what we know about the universe for spaceborne telescopes mainly, is from light and infrared. Light and infrared spectrum. What AMS will tell us is a charged particle perspective of what we see in space. We have a bunch of theories, and we know, well, we think we know what the universe is telling us. What we will know after AMS is we'll have a definitive measurement of what is coming from the beginnings of the universe, what is coming from distant galaxies, what is coming from from pulsars, etc. And so, as you measure the data, you say, well, does it match with the existing knowledge, or does it not? And you're actually more interested in when it doesn't match with the existing knowledge. If it doesn't match the existing model, you found something new, maybe someone on AMS wins another Nobel Prize.
Over here. Hi, I'm actor Dr. Lucy Rogers. You're looking for cosmic particles up there. How do you know they're going to be there? How do you manage to test it here, and how many are you going to find?
Okay. That's a pretty easy question. I can actually answer that. So AMS has been tested on the ground. We built it at CERN in Geneva. We actually put it into the particle beam at CERN, and we shot particles through the detector and calibrated the experiment so that we know a given set of particles at a given set of energies, this is what you're going to see in the detector. We then brought it here to Kennedy Space Center, put it over in the Space Station Processing Facility, pointed it upright, turned it on, and we measured 400 hits of particles every second. When we get to space, we'll see 25,000 hits every second. And the reason for that, Earth's atmosphere tends to absorb all of those particles, which is why we need to do this science in space.
Any more questions? I got some. You and then we'll go.
Hi. I wanted to know how difficult it was or what challenges you ran into trying to make it all fit on the shuttle so you could get it up to the ISS.
That's a really good question. The first time I went to CERN, they took me down into the tunnel of CERN. And CERN has 4 major experiments. Each one of them weighs hundreds of thousands of pounds, is 6 stories high, and they said, we want to make that into a littler version and launch it into space. That's a difficult task. And in fact, that was the job of my team at the Johnson Space Center. Our job was to go with the scientists, figure out what they wanted to put up there, figure out a way to shrink it down to the right size, make sure that it had enough redundancy that you could survive in space. And as Professor Ting says, since you can't send a grad student out to go fix it, it better work. So we worked with them over the last 17 years. We developed numerous new electronic systems that are specifically built for AMS, much faster electronics than anything we've ever built for aerospace before. And already we're seeing 25,000 hits every second, which means we're getting that much data coming into our computer. We see 7 gigabits of data per second. We have to use our onboard computers to speed that down to only 6 megabits per second, because that's all we're allowed to send down from the space station.
Would you like to see the AMS?
So yes, there are a few challenges in making this happen, but you put the right high-energy physicists together with the right aerospace engineers, and you get an AMS.
Okay. Let's see if I can explain. If I understand this correctly. It's observing cosmic particles, and if I understand that, it's like there are some Earth-based things that observe that. It's tricky that the particles go through pretty much everything. Is that correct? And is there something in the design for AMS that can make it do that easily, or is it just observing particles as they're flying through and not capturing them?
Okay, so the way I like to describe the detectors that are in AMS is if you went to a high-energy physicist and you said, if you want to measure cosmic rays or charged particles, what detectors would you choose? They would pick every single one that we put on the AMS. So we're utilizing the same technology that we use on the ground to do these measurements in a beam, like at CERN, or at Fermi Lab, or at Brookhaven. we're doing it in space. And instead of utilizing that beam as our accelerator, we're utilizing the universe as our accelerator. And the universe is the ultimate accelerator. So the energies that we'll see in space are much higher, in fact the highest that we could possibly imagine, because it is the universe accelerating those particles for us. I don't know if that really answers your question. Does that answer your question?
Okay, thank you. You know, I just have a quick question for you. I heard that it could potentially, AMS could disprove string theory, not necessarily prove it. Is that? Could you explain that?
Now you're getting into science questions. And I forgot to tell you that I'm an aerospace engineer and an MBA. I've reached my limit of science, especially when you start talking string theory. So,
well, that's kind of the exciting things that AMS could have in store for us. Thank you, Troy. I appreciate your time.
all right, thanks.
If you have those experiments that Tara passed around, please bring them to one of the people with the blue badge so we can get them to her. We're going to break for the tours. You need to be at the buses pretty soon. Some advice I'm going to give everybody is please bring bug spray. It's a lot of people think we're joking, but you will get eaten alive.
That's okay. It was glued on yesterday.
We don't want to go off the launch pad. There's some time, if your cars are out there, drop your stuff in your car. Obviously, you want to keep your smartphone with you if possible to still stay connected. But that ends the formal presentation of the tweet up. Thank you for joining us.
Just a reminder, guys, regarding the buses and the tours, you can get on any bus you want the first time. After that, you're committed. So get back on the same bus that you get on the first time each time, and make sure that one of us checks you off as you get on the bus. We want to do this so that we don't leave you somewhere. Thank you.
Do you have the same battery I do? No, I have the charger. Probably have.
Yay, fully charged.
To get out there and be surprised. Pop it full of these.
No, not yet. I didn't pre-order. So I was going to grab one large or extra large? Okay, so I'll do an extra. It's 20. 20, right? Yep.
Are you gonna?